Welcome to Math-A-Thon episode 3. So, if you haven't watched episode 1 and 2, which are like both over 2 hours long, you are fine. You are perfectly understood. I'm covering real analysis stuff, and yet again, not as a teacher, but just as a student, solving problems. Since I have a midterm coming up pretty soon, I'm simply just going through problems that were covered in class at some point a while ago, just to make sure that I at least know how to solve stuff. Okay, we already did a bunch of stuff on, well, that was a series. No, that's sequences. Yes, we did a bunch of stuff on sequences. Now we are starting today with series. Okay. Sorry, I just ate and I might be a little bit gassy, so sorry. If I'm able to scroll back to my content, there we go. So technically, this one part of it, at the very least, I already did. Because this is actually my take 2 at recording this. Yesterday I did a few of them. It took quite a while. Where is the sheet? It took quite a while. And then like my little bro came in, and I'm like, yeah, I'm not posting online a video with him in it, so I'm just I'm gonna have to just redo it. So but where is it? Oh, there it is. Wow, it took a while. So a lot of these, a few of them, like this one and this one this one was hard. This one I'm not gonna do it, mostly because I don't think it's gonna be covered. So yeah, it's mostly just gonna be blitzing through that stuff, through the stuff that will be covered, and then we'll go to something else. So I got my timers as usual. I work in sets of 90 minutes. Take a break, and then after that we'll see how long we go. I imagine that with explanations, it might take I don't know, and I won't advance myself too much. So let me just set the timer here. Oh, well, okay. My screen decided that it would be 1 minute 35. So there we go. 1 hour 35, what I'm saying. So okay, we start with this one. We have Sn. We have our summation here defined as follows, which is the harmonic series. Okay, and we want to show that the second power, okay, the sequence to the second power, is greater than or equal to 1 plus n over 2. Okay. In other words, if I write that out, it's probably obvious enough, but just in case, I have 1 over 2 plus 2 all the way to 1 over 2 to the n. Okay, that is less than or equal to 1 plus n over 2. Okay, so that's what we're trying to show. Whenever we have something like that, where we have some something in terms of n, and then we have like this conspicuous for all n here, you will probably need to do induction. And in this case, if there's other ways to do it, I don't know, but the way that makes the most sense is to do it with induction. So you start with, as you usually do in induction, you start with showing a base case. Okay, so base case, we said for all n, so start with n equal to 1. Okay, for with n equal to 1, we're gonna have s to the 2, which means that we stop here. And that ends up being exactly, and then we have 1 over 2 here, so that ends up being exactly 1/2 on both sides. Okay, so we have 1.5, which is greater than or equal to 1.5. So we're Gucci with that. Then what do we need to do? We need to first write the induction hypothesis. Okay, The idea of induction, for those that don't know, which, well, would be kind of surprising if you're watching a real analysis video, or maybe it might not, I'm not too sure, but anyways, it's using the well-ordering principle and the idea that for any set of real numbers, okay, you're gonna have a smallest number. You started by showing some base case. Your base case is, well, this based on that smallest number that you care about. And then from that set of natural numbers, since typically you're going to be working with sets of natural numbers that make sense, so like you're not going to be picking up an arbitrary set, you're going to have something like, let's say, the even numbers, the odd numbers, all of them, something along those lines, powers of 2 maybe, or just powers, for example. Well, by starting with some value of n here, there's going to be a natural way to go to the next, like to find the successor of that value of n, and then that value, etc., etc. And so if you're able to show it for a base case, which we did already here, if you're able to show whatever property you're trying to show for some base case, you assume it for some arbitrary value of n, and then are able to show that it holds for n plus 1 as well, so for its successor. N plus 1 or whatever makes sense in your context, but typically it's going to be n plus 1. Then since you have the base case, so some n, and you showed it for the successor, then it's just gonna hold for everything from there. That's the idea of induction. Okay, and here we already showed the base case, so all we need now is to assume the property we want for n, which is, well, just the question that is asked. So we're going to assume that 1 plus 1 over 2 plus 1 over 2n is less than or equal to 1 plus n plus 2, n over 2. And we want to show, okay, that this means that 1 plus 1 over 2 plus 1 over 2, here we have n plus 1, okay, is less than or equal to 1 plus n plus 1 over 2, okay? So for these kind of problems, a lot of time it's really just a matter of affecting one side, whichever it ends up being, and then transforming the other side so that it works. And sometimes the step that you need to do is complex, sometimes it's simpler. In this case, it's like, it took me a while to find it when I did it the first time. Like, I spent at least 30 minutes just thinking about it. And at some point, you're just like, oh, wait, yeah, I can do that. And that's, sometimes it takes just a lot of time. But yeah, in this case, what can you do? Well, it always starts with just affecting one side. In this case, here, it's, when we start from this base case here, I don't see how to go by adding something from this to this, right? Okay, I don't see in one step by adding one thing how I can go from this to this. But what I do see is that I can go pretty easily from this to this, right? And so what I'm gonna do first is just start yet again with what we assume to be true, and then I add 1 over 2 to that. Okay, because like this here is really just that, right? And to keep the inequality the same, now I need to add 1 plus 1 over 2 here. Okay, so now I have, well, this part stays the same. All of this stays the same, pretty much. Okay, and on this side now, I have what I need. N plus 1 over 2. Okay, so now the thing is, here, I have 1 over 2 to the n, and plus 1 over 2. This 1 over 2 here is not what I want. What I want is, well, here, embedded, like, implied, I already have 2 to the n here, right? And then I have, well, this, okay, plus 1, and then all the way to that here. Okay, so what I have is this. Oops. Okay, well, that's fine. Let's put that back to black. What I have is that part here. What I want is all of this. Okay, because we already have the 1 to n here. Okay, let me just remove the brackets for consistency. So now, then the natural next step is to try to show that this here is greater than or equal to 1 over 2. Right? Because if I'm here, I added something and I have an inequality. If I add 1 over 2, at least 1 over 2 here, then I maintain the inequality as well. So if I'm able to show that just that here in general is greater than 1 over 2, I am good. If you start naively with 1, like with n at 1, it's not naive, it's just like the natural thing to do, pun not intended, you will get something that doesn't work. Yeah, it won't work because you will have just, wait, actually will it not work? You would have, wait, let's see, 2 to the n would be 2 itself, wait, I have 1, 2 to the n, oh wait, no, actually it does work. No, because you're trying to go to n plus 1. So if you start at n 0, you're going to have 1 plus 1 over 3 plus 1 over 4. No, because that's for n plus 1. Yeah, no, it does work. What am I saying? Yes, it does work. Wait. Yes, it does work. Let me just double check my math here. Like it does work. Yes, it does work. Okay, no, never mind. You can start at yes, you can. What I did right now was weird because I started at n over 2 anyways. But you can start at n over 1 because if you start at n over 1, okay. We just started. I'm not supposed to be tired already. Well, it's 8, so I guess. So I start at 2. So the next term will be that. Yes, okay, it does work. I think it does work. So, yes. Never mind. I can use 2. And if I do that, well, I'm going to have I'm going to have 0.58 roughly for n, which is greater than 1 than 0.5. Okay? So I showed my base case. And honestly, I don't even need to show a base case quite honestly, because that assumes an induction proof. That assumes an induction proof. But there's something much simpler that we can do here. Okay? Here, I can show it to the side and then just, I'm going to use that observation. Okay? If I start from some power of n plus 1 to the next power of n, okay, there's gonna be exactly 2 to the n terms, okay? And what do I mean by that? Here you see that I started by 2 to the n, okay, plus 1, and then I go all the way to 2 to the n plus 1. So say I go from 2, okay? Well, when I consider 1 over 3 to 1 over 4, I have 2 terms here. Okay? That's my 2 to the n plus 1, and that's my second power. I have 2 terms here. If I consider 1, like I go to the 8, no, I'm not doing to the 8, but I do to the 4, for example. Okay? Then 4 is 2 to the 2, and then I'm going to have 1 over 5, 1 over 6, 1 over 7, and 1 over 8. And as expected, boom, I'm gonna have 4 terms here, which is the same as that. And so this is a general pattern that's gonna hold because that's just the way we count stuff. That's just the way powers of 2 work. Okay? And so here, even though it might not be obvious, there are 2 to the n terms here. And so now the thing that I can do to show that, well, to show without induction that this proof, that this thing is true, okay, is, well, something really similar to actually to how you prove that the harmonic series diverges. Okay, it's actually the same thing. Okay, and what do? Is you take each, you realize that here this is the biggest term of this entire summation. Okay, because it has the smallest denominator. This is the smallest term of this entire summation, which means that if I replace all of those terms here by what is in here, okay, like each of those 2 n terms by that, then I will have something that is strictly, well, less than that. Okay, and so that means that I can write that as I can take my mouse here. I can do the following. So let me copy that part. Okay, I can copy that and replace each term by that. Okay, which means that I'm gonna have that plus which is, as we said, there's 2 n terms, right? So I'm gonna have 2 to the n over 2 to the n plus 1. Okay, which is, well, quite exactly 1 over 2. And so boom, without having to use induction, we've shown that indeed this part here is just strictly less than 1 over 2. And since we showed that, well, it means that without any more work to do, okay, we can replace the 1 over 2 that we have here by this missing part. And so we have that. We replace it. Well, I guess I'm just gonna do it on a new line. Okay. And then I have my, well, this part didn't change. Okay. And boom, that is exactly what we wanted to show, in the sense that, like, we managed to do the inductive step. Okay. And since we managed to do the inductive step, then, well, we succeeded in the induction. So since we succeeded in the inductive step, is it inductive leap? Oh, one of the two. I don't remember the exact term, but it's fine. Since we succeeded in the inductive step, we showed by induction the property, and that's it, shown. Like square. I typed that as if there was math jacks here, but anyways. Well, now we get to this. We already spent a bit, like almost 15 minutes on that. Well, no, actually we didn't. How long have we been going here? Oh, it doesn't matter, does it? Okay. So now, next part is this series, okay? Well, for series stuff, typically what you want to do is the divergence test, okay? In this case, if you do the divergence test, well, you can just like squint and see that you're gonna have 1, and the limit of log to the 1 is gonna be, like, this is gonna be 0, okay? So it doesn't fail the divergence test. So the next step now is, well, try to find a pattern to the thing, okay? Analyze S1, S2, S3, work with the partial terms, or with the partial sums, okay? In this case, well, that's what you do if there's not some other obvious thing that you can do to it, like compare with like a p-series or geometric or whatever, and like show that they have the same behavior. In this case, there's no obvious thing I can compare it to. At least I can think of one, and so I'm using the partial sums. And so, does it diverge? Does it converge? I don't know, but well, no, actually I do know, but let's just work out the sum, okay? So here we have, well, log to the 1, log to the place 1 here, so we're gonna have log to the 2. For s over 2, we're gonna have log to the, well, we're gonna have 2, same part, same thing as above. But now we add a new term, we plug 2 in there, and so we're gonna have 3 on top, and 2 on the bottom, okay? But by properties of logarithms, if you have a summation of logarithms with the same base, you can multiply the inside. So that means that we have log of, well, log of 3, since the 2 cancel. And, well, if I do the same thing with S3, you see how this would just be log of, well, it would just be S2 plus a new term, which would be itself 4, okay, 4 over 3, and then the 3, this would cancel, and so we'd get S of 3 equal to log 4. And so the pattern is that we're going to have S of n is equal to, well, log n plus 1. And so now, take the limit as n approaches infinity of log of n plus 1. This is obviously going to diverge, okay? And if you need to show that, well, it's going to diverge to infinity specifically, okay? And if you need to be rigorous, with that, well, you just need to show that for all m greater than 0, there exists some n such that if n is greater than n, okay, then m is less than log to the n plus 1 pretty much, okay, plus 1, since those are the terms of the sequence, okay, which can be, we can write that proof fairly simply by just starting from what we want to show and working backwards. So if m is less than log n plus 1, it implies that e to the m is less than n plus 1, which then implies that e to the m minus 1 is less than n, okay? And so since we want our n to be a natural number, we're going to take the ceiling of e to the m minus 1. And since m is assumed to be a big number, the ceiling here is going to be a natural number. I don't need to do more than that to it, okay? And so we're going to set n to be that, okay? Set n to be equal to that, okay? And so now we can actually write the proof. For we claim log n plus 1 diverges to infinity. This means definition. And I'm not writing it twice because I already have it above, okay? For all m greater than 0, for any m greater than 0, set n to be the ceiling of e to the m minus 1, okay? Then for all n greater than m, then n, we have ceiling here e to the m minus 1, okay? Well, clearly this is going to be less than or equal to just the inside of the ceiling function, right? And on this side we have a strict inequality with n. Oh, whoops. On this side we have a strict inequality with n, okay? Now, what can I do with that? Well, I can just reduce it to what we care about, which is this part, okay? And then add 1 to both sides, e to the m n plus 1, and then finally just take the logarithm of both sides, which will give me m and log n plus 1, which holds for any m. And so, yeah, by that, we showed that log n plus 1 diverges to infinity. So now the only place, so like that'd be good. We show that it diverges. The only place really where we could have fucked up is like here, if somehow I use the wrong property of the log. The property of the logs I use doesn't exist, but I'm pretty sure it does. So yeah, we're gonna do that. Here, when I saw it for the first time, I was really confused what exactly to do. But the trick here is just to realize that, well, here you have r squared minus 1, okay? Then, if that is true, then you can, like, this is a difference of square. This is because of the fact that we have a difference of square here that I can rewrite as 2 over r minus 1, r plus 1. And then when I do the partial, fraction decomposition thing, I'm gonna get that. Okay, that's how we get that. Okay, well, if this holds for that, okay, where I divide by the top by 2 and I have the term here, well, if I do the same thing for r to the 4th minus 1 like that, this is still a difference of squares. Okay, this is now r to the 2 squared minus 1 squared. Okay, which means that I can do 2r squared minus 1. Oh shoot, my timer is, my phone is dead. Okay, so let me put okay, I'll put a timer for 1 hour. I'll put a timer for 1 hour. Okay. We will have finished it before the end of the 1 hour, but yeah. Okay. So let me see if my OBS is recording properly. Yes, it is. So we have that. So I can do that, and then I'm gonna have r squared r plus 1 here. Okay. And so this is the term I'm looking for. This is the term I'm looking for here. Okay. And each time you're going to see that, well, this 2 to the r minus 1 here can be expressed as that. I can send that. Well, it makes more sense to just do it, to just write it right now. It makes more sense to just write it. But the idea is there. So if I send that to this side now, okay, I'm going to have 1 over 1 r plus 1, which is what I was looking for here, 2r squared minus 1. Okay. Now, this term here, I can express it as something in terms of that. And then something in terms of that will be expressed in terms of that. And then that's why you get the dot, dot, dot. So I'm just going to show the first few steps. And then I think I will have showed it. So, yeah. So, 1 over r minus 1 by the int is equal to 2 over r squared. 2 over r squared minus 1 plus 1 over r plus 1. Okay, so we don't need to touch this part because it's already as we want it. But this part here, what can we do with it? Well, we can do with it, just observe that we have 4 to the r squared there, which is 4 to the r 4 to the r 4 plus 1 minus 1. Okay, minus 1 is likewise going to be equal to 2 to the r squared minus 1 plus minus what? Minus 2 to the r squared plus 1. If I didn't mess that. Yes, I'm pretty sure, so that's fine. Okay, which means that if I rearrange that that equality here, I'm gonna have this term here equal to, let's just, now I just change the sides, and then this now is a plus, okay, because all I did was changing this adding that to both sides. Okay, and so that means that I can replace what I have here by that. Okay, and so here as well, for consistency with what we with what was given. Okay, I have this, but this is equal to this, and then what we found here, which is equal to that. Okay, and then same thing, we just rearrange that. Okay, and while likewise this term here will be equal to something else, so I'm just going to stop at this point, in terms of 8, and then the term that we want positive, and then just going to go to infinity. So that's the idea, and that's just what you keep doing recursively. So now find the sum of the series. When looking at series, again, the idea is first you start by doing the divergence test. Here in this case, we have some constant on top, a bunch of k's on the bottom, which is what we're making vary. So this is the individual terms will be going to 0. Okay, so it's not gonna be an issue. So what do we do next? Typically for these kind of problems, if you see that you have something on top, like some constant maybe, and then something on the bottom where like everything is either, it can be, you can find like a factorization, like here you can write it that way, or it is already given to you, it's a telltale sign that you're supposed to use well, you will be praying that it's a telescoping series. It most of the time is. Okay, in this case, what do? Well, if you have something of the form, I'm gonna do that in a proper note here because I think it's gonna be clear of the math notation. Okay, for it to be clear, I need to like actually do it properly. Okay, there we go. So we'll do a big and a line. There we go. Okay, so if we have the fraction 1 here, and it was k plus 2, k plus 4. Like, for a funny story, I did part of this yesterday in my head as I was going to sleep, because like I actually didn't solve it in one go. Okay. And I had forgotten how to deal with like telescoping series and like do the partial decompositions and stuff when like you have more than 2 terms on the bottom, and I just did part of it in my head, and so like now I just remembered that thing. Well, I don't know how insightful information that was, but this is equal to sum A. Okay. And here, like, it's boom. So B, C, and don't worry, I know we're not done yet. With part here, this part here, and this part here. Okay. Oh, whoops, I did that wrong. Ah, shit. So it's equal to that. Okay. So it's gonna be equal to sum A on some fraction in terms of k, some fraction in terms of k, some fraction in terms of b here, like that. Okay. Well, here what can I do? I can multiply the numerator here. I can numerate both. I can't speak anymore. I can multiply both sides by the denominator. If I do that, on this side I'm going to be left with the numerator, which just happens to be 1, so that's really nice. And then here, it's going to cancel part of the terms. Okay. Well, it's going to cancel the fractions just in general. And I'm going to be left with, I need a ampersand here. I'm going to have 1 here, A, well, the k is cancelled, so what's left is k plus 2 and k plus 4. Okay. If it will, yes. For the B, let me align that. Okay. For the B, the k plus 2 is cancelled, so I'm gonna have k and k plus 4. K plus 4. And finally, for the last one, I'm gonna have just c, k, and k plus 2. Friggin'. Okay, so now that we have this form here, it's a matter of just setting different values of k strategically in such a way that I only have to care about one specific like coefficient, a, b, or c. Okay. Let's start with text here. Let's set first k equal to well, a smart one would be -2. Why -2? K over 2 is shared by a and c. So if I set k -2, it cancels both of these and I'm only left with the middle term, right? So I'm gonna do that. Okay, and I'm gonna do the text align on that. Okay, which means that we're gonna have 1 equal to b minus 2 plus 4, yes. Okay, which implies, okay, I have -2, I have 2, so I'm gonna have -4, which implies that b is equal to -1/4. Okay, -1/4. And let me put the minus in front of the fraction. Okay, so that's part 1. Let's do the same thing, but now set to a different value. A sensible one, since we have like a floating k, let's just set k to 0. Okay, actually would have made, yeah, it makes sense, it goes in order. So let's set k equal to 0. In this case, all the terms with a simple, like with a floating k will be cancelled. So this will be cancelled, this will be cancelled, so what's left is a. And so we have, well, this is convenient, this. Okay, and since it's set to 0, we have that here. Okay, which, well, implies that a is equal to 1/8. Okay, and then finally we have k plus 4, so the natural choice would be k -4. So actually no, I should have done this one first maybe. So let's do that here, just so that we have a proper order that makes sense. And so this term will be cancelled when we set it to -4. This term will be cancelled, and so what's left is c. And so yeah, we have a nice order. I like it. We have like a decreasing orders type of thing. Okay, and so we have -4 here. We have -4 here. Okay, so we're gonna have -2 times -4, which is 8, right? And then we have this implies that c is equal to 1/8 as well. Okay, so now this we have 1/8, 1/8. We have something that is almost nice, so that we have everything that is, well, it is nice. We can already work with that, but since we have an 8, 8 here, might as well put that on 8 as well. And so we're gonna have 2/8 here. Okay, -2/8. Sorry. Okay, and so if we take this here, okay, well, we might as well take this full thing here. Okay, we have that this is equal to 1. Let me pull the 1/8 outside entirely, which is why I did what I did. Okay, and let's put a big here. Yes, that's slightly neater, I guess. Okay, so we have 1/k. We have b here, which is 2/8. The 8th is outside, so we have just 2 inside, and we have a negative. Okay, and then finally we have 1 here. Okay, and since that was for a single term, then the sequence is sum of k equal 1 all the way to, well, infinity, I guess. Okay. Wait, what did I do? What is it complaining about? There we go. There we go. Okay. We have the sum of that here. Okay. And maybe we want to align that as well. Yeah, that's good enough. Okay. And, well, here the 1/8 is going to be common to all the terms, so might as well just take it outside the fraction, right? So, yeah, maybe I should put, yeah, that's fine, that's fine. So I'm gonna have, okay, you know what? For completeness, this is just for my own sake here. I'm gonna do this, rewrite it properly from this summation. This is just for my own sanity here. There we go. Okay, now it's nice. So if you'll excuse that, yes, and I can take the 1/8 outside of the summation. Okay. 1/8 outside of summation, like that. Boom. Okay, since it's gonna be common to all of the terms anyways. Okay, which means that now we have a somewhat of a closed form to work with. Okay, so now the next step will be to work with, well, try to find the general form of Sn. Okay, so Sn is equal to 1/8 frac of 1/8. Okay. Times, and now I'm gonna put a, I'm gonna do it line by line because it's much simpler when you keep each k on its thing to do the cancellation. Like, you don't need to like keep looking ahead, you can just like look, well, downwards essentially. Okay, and so the first line will be for the k equal to 1, second line k equal to 2, and I guess I need to do the lines here. I need an align as well. So we'll do and align. Okay, and they'll all be aligned on the equal sign. No, I guess I want them aligned here. Yeah, I guess I'll do that. So yeah, sorry. Right now I'm just like thinking about like the logistic of my writing the expression here. Okay, I think it's gonna work. So if I do 1 here with 1, I'm gonna have 1 minus 2 minus frac of 2, 3, and I'm gonna have plus what here? Plus 1/5. It took a while. Okay. If I do the second line, okay, I'm gonna have the fraction of 1/2 now. Okay, and I guess I could, to keep the same format everywhere, write it that way: 1/1, 1/2, and here this, when I put 2 here, I have 4, and when I put 2 here, I have 6, and then you should be able to see that, okay, this is going to be, the denominator is going to be counting, kind of, so we have the harmonic series on the first column. This one is going to be counting the denominator going from 3, 4, 5, 6. This one is going to be going from, well, 5, 6, 7, 8, blah, blah, blah. So I'm going to do a few rows, and I'm doing a bunch of rows like that because, well, in this case, I know that it takes a few rows to like see the cancellations happening. So we have 3, 5, 7, 4, 6, 8, 5, 7, 9, 6, 8, 10. Okay, and then, well, at this point, I guess I'm gonna do a v dot thing. V dot. Oh, is it v dots? Yes, v dots. Okay, and go from the end. Okay, so if we stopped at, well, n, because that's what we're considering here, when I have n, we see that it's n plus 2, so it's, I can just write n plus 2, and it's n plus 4, so I can just do n plus 4. Okay. Then if I work backwards, like strictly I don't need to do that because I see already that a few of those terms will be cancelled. But well, no, actually it might make sense to do that. So okay, so now what do? Work backwards. So let me add let's do that. Now, because before we start seeing cancellation, it's gonna be annoying. Okay, I'm not gonna bother doing those n terms. Why? Because when I take the limit, all of those n terms will be going to 0 anyways. So it doesn't really matter. Okay, what is important is, well, oh wait, no, actually they might matter. They might matter because if this, no, the entire thing goes to 0. Yes. Okay, so since we have this form here, if we have something like with n on top where like the n might actually contribute something, then it doesn't really matter. Then we might want to actually take care of those. But here, since we have n on the bottom, when the n goes to infinity, the entire fraction is going to go to infinity. So we don't need to be too worried about this part. So now, when we focus on this here, okay, maybe if I'm able to like take a screenshot. Can I take a screenshot on this computer? Oh yes, I can. Nice. I'm on like Kali Linux right now, so like there's a bunch of stuff that like I just haven't checked if I can do yet. So let's just paste this here and oh frick. Where does that go? Paste. Did it paste an image? Okay, well, I guess I'm just gonna need to work it out here. Okay, well, you can see, if you can see my cursor, that this 1.5 here, okay, and this 1.5 here will cancel with this 2.5. Okay, so I guess I can just like literally just erase them as I mention it. So this 1.5 cancels with this 2.5 and this 1.5. Okay. This 1.6 will cancel with this 2.6 and then this 1.6 here. So 1.6, 2.6, and then the 1.6 that is here. Okay, and then you can see that for the foreseeable future, all those 1.7, 1.8, 1.10 will be cancelled by something inside. So we can just erase those already. Okay. I wish I had a better way to, well, display that, but sadly I don't. Okay. Now, sorry. For what that is left, the 2.7, the 2.728 as well must be cancelled because, well, 1.727. So the 2.7 is gone as well. 2.8 is gone as well. And why are they gone? Because, well, the 1.7 is cancelled by the fact that the 2.7 cancels it partly by this and partly by something inside, partly by this and something inside. So now we have this part here of the stuff that is left. Okay, everything else is going to be cancelled by something inside. And then we get to the nth term, okay? But as n goes to infinity, those terms will just go to 0. So we don't really need to worry too much about them. which means that all things considered, the only things that really matter is, well, the terms that are left. So if I rewrite that, if I write that without the beginner line, maybe. Okay. Okay, yeah, it won't display properly because of the times. Boom, okay. This is the limit, okay? This is the limit, okay? That's why I didn't copy 2 infinity. Okay. This is the limit part because all of this as n goes to infinity will go to 0, so I don't need to worry about those. The only terms that are important in the end is like what is here. And so we have, well, that. Okay. Boom. And yeah, that's it. That's the answer. That's the answer. So now if I don't need those anymore either. Okay. And so now if I just paste that into Symbolab, for example, because I don't feel like computing this manually. Okay. I will get some nice fraction that we can then express. Whoops. This 1/3 is left. Okay, so 1/3 here, and then it's plus like that. Yeah, that it makes a little bit more sense. Did I clean up my equation properly now? Yes, I think it is. And so let's check the answer in Symbolab, and we get 11/96, and boom, that's the answer to that sum, assuming I didn't make a mistake anywhere. And so yes, amazing. So that is essentially, I'll scroll back to content. Why does it keep bringing me here? Okay, where are the others? There's like a world between them. Lol. Okay. And so the answer to that is, assuming according to our calculations, 11/96. Beautiful. Okay. And so all we needed to use here is the telescoping series trick, like the partial fraction decomposition. Okay. Okay, so that's pretty great. We finished in less than an hour, which is amazing. So I guess I will take an early break since I was able to like finish early. That's my reward. And so I'll charge my phone, and I'll see you in the very next video on Math-A-Thon. So yes. Thanks for watching. God bless.